All right, good morning, guys. Today we're going to be covering 9.3 Hero's, also known as Heron's formula, and Brahmagupta's formula as well. So let's go ahead and jump right in. First off, we're going to start with Heron's formula. It's also known as Hero's formula. Now, Heron's formula was discovered about 2,000 years ago by the hero of Alexandria. Now, it's also known as Heron's formula, and that could just be due to a pronunciation of hero. Now, this was used to discover area of triangles. So this can be used to find any area of any triangle as long as you have all three sides of that triangle. So again, it's only going to be used with side, side, side. So when you have all three sides of a triangle, that's when you can use Heron's formula to find the area of that triangle. Now, Heron's formula is area is equal to the square root of s times s minus a times s minus b times s minus c, where a, b, and c are the side lengths of our triangle. And further, the variable s, this is a new variable for us. S is going to be the semi-perimeter, and that's going to be the same for anything within 9.3. S will always be the semi-perimeter. And in order to find the semi-perimeter, well, that would just be half of the perimeter. Now, the perimeter is the distance all the way around a shape. So if I want the semi-perimeter, if I want half of it, I just add up my perimeter, so I add up all sides, and then I divide it by 2 to get half of that distance. So that's how we're going to use Heron's formula. The other formula that we have is Brahmagupta's formula. Now, this was recorded in 628 CE by a Hindu mathematician named Brahmagupta. This is used to find the area of an inscribed quadrilateral. So again, an inscribed quadrilateral just means that's inside of a circle. And we can see that right here. Each point is on the circle for our quadrilateral. So we have all 4 vertices on the circle. These quadrilaterals are commonly known as cyclic quadrilaterals. So that's something that you're going to see fairly often where they're saying that area of cyclic quadrilaterals. That's when you know that you're going to use Brahmagupta's formula. Now, Brahmagupta's formula is very, very similar to Heron's formula. There's just one slight difference. So, Brahmagupta's formula is area is equal to the square root of s minus a times s minus b times s minus c times s minus d. Now, the main difference here is that I'm not multiplying by the semi-perimeter out front here. And also, I have a 4th side this time. So that's where this takes place, is this 4th side here. Now, same thing occurs. A, B, C, and D are all the sides of a quadrilateral, and S is still the semi-perimeter. But this time our semi-perimeter formula is slightly different. And the reason for that is because we have 4 sides now instead of 3. So it's the same thing, it's half the perimeter. So I'd have to find the perimeter by adding all 4 sides together and then dividing by 2. And that will still work in solving for the semi-perimeter of a quadrilateral. So let's go ahead and try out some examples using Heron's formula and Brahmagupta's formula. Starting up with Heron's formula, we want to find the area of a triangle with sides 3, 6, and 7. So, of course, we're going to use Heron's formula here because we have a triangle. And further, we see that we have side, side, side. So step 1 will always be to find the semi-perimeter of the triangle, or the shape. In this case, it's a triangle, so to find that, we just add all 3 sides together, and then we divide it by 2. So 3 plus 7 is 10, 10 plus 6 is 16, and half of 16 will leave us with 8. So our semi-perimeter is equal to 8 units. Once I have the semi-perimeter, I can plug it into Heron's formula to solve for the area. So that'll be the square root of s times s minus a times s minus b times s minus c. Plugging in 8 for s, and then I can plug in 3, 6, and 7 for a, b, and c. It doesn't matter which number goes in for which because we're multiplying, so the end result will be the same. So again, I can say that 7 is a, or I can say that 7 is c. It doesn't matter which one you say is 7, as long as each side gets its own variable. So plugging in all of our variables, we're left with the square root of 8 times 8 minus 3 times 8 minus 6 times 8 minus 7. Now, if you enter this into your calculator, you'll get your exact answer right away. But I'm going to go ahead and do the math and further this out. So 8 minus 3 is 5, 8 minus 6 is 2, 8 minus 7 is 1. Well, 8 times 5 is 40, and 40 times 2 is 80. 80 times 1 is just 80, so therefore this will be equal to the square root of 80, which if we simplified is 4 radical 5 units squared, or 8.94 units squared. So these are our answers for the area of this triangle. Next up, we want to find the area of the inscribed quadrilateral with sides 2, 7, 6, and 9. So our steps are very similar this time. Now, this is an inscribed quadrilateral, so which formula would we use? Heron's formula or Brahmagupta's formula? Well, in this case, since it is a cyclic quadrilateral, we're going to use Brahmagupta's formula. And so our first step should be to find our semi-perimeter, S. So same exact steps. So solving for S, I add up all my sides, and then I divide by 2. 7 plus 2 is 9. 9 plus 6 is 15. 15 plus 9 is 24. Half of 24 will leave us with 12. So our semi-perimeter of this cyclic quadrilateral is 12 units. Next, I plug this in to Brahmagupta's formula. And again, keep track of those slight differences in the formulas because those are important for us. So Brahmagupta's formula is area is equal to the square root of S minus A times S minus B times S minus C times S minus D. Plugging in our sides for A, B, C, and D, and plugging 12 in for S, we'll be left with the square root of 12 minus 2 times 12 minus 7 times 12 minus 9 times 12 minus 6. If you enter all of this into your calculator, it'll give you your exact answer right away. But you can also simplify this down further. 12 minus 2 is 10, 12 minus 7 is 5, 12 minus 9 is 3, and 12 minus 6 is 6. From here, well, 10 times 5 is 50. 50 times 3 is 150, and 150 times 6 is 900. The square root of 900 will give us 30 units squared for the area of our cyclic quadrilateral. Lastly, I have one last difficult problem for you guys. So we want to find the area of the pentagon to the nearest tenth. Now, first off, is this pentagon a quadrilateral? No. Again, a quadrilateral has 4 sides to it. And as we can see, this pentagon has 5 sides. So no, this is not a quadrilateral, so I can't use Brahmagupta's formula. So if that's the case, we need to find a workaround. So the first thing I'm going to do is I'm going to draw an auxiliary line, and this auxiliary line will be used to create a quadrilateral and a triangle. So think about where we should draw that in. Well, a big hint for us is this right angle here. If I draw my auxiliary line so that I create a right triangle, that will be very easy for us to solve with. So I'm going to go ahead and create my auxiliary line right here. And I'll go ahead and label that auxiliary line as X. Now that we have X, we can go ahead and solve for it. So to solve for this missing side length, I can use the right triangle down here. I have 2 known sides and a missing side. So using Pythagorean's theorem, I'll have 6 squared plus 8 squared equals x squared. 8 squared is 64, 6 squared is 36, 64 plus 36 is equal to 100. So 100 equals x squared. From here, we can take the square root of both sides, leaving us with x equals 10. Now, of course, this is a Pythagorean triple. This is a special 6, 8, 10 triangle, so you may be able to look at this and know that this is 10 right away without actually having to do this math. But that's if you are able to identify those Pythagorean triples. Now that we know that x is 10, we can go ahead and solve for the area of these 2 figures, because now I have a cyclic quadrilateral up top with this trapezoid, and I also have a triangle down below with this right triangle. Now I'm going to go ahead and use Heron's formula and Brahmagupta's formula, even though I can use just the area of a triangle here to solve. And the reason I'm going to do that is because we need to make sure that we're practicing with it. So first off, using Heron's formula, again, is the square root of s times s minus a times s minus b times s minus c. But the first thing that I need to solve for is s, and I'm solving for s within the right triangle. So to solve for s, I would do 8 plus 6, which is 14, 14 plus 10, which is 24. Half of 24 will give me my semiperimeter, so therefore my semiperimeter is 12 units. Once I have my semiperimeter, I can go ahead and plug that in for s, and then I'm going to plug in 6, 8, and 10 for a, b, and c. So I'm left with the square root of 12 times 12 minus 10 times 12 minus 6 times 12 minus 8. If you enter this into your calculator, you'll get your final answer for the area of this triangle right away. Simplifying it down further though, 12 minus 10 is 2, 12 minus 6 is 6, and 12 minus 8 is 4. From here, well, 2 times 6 is 12. 12 times 12 is 144. 144 times 4 is 576. The square root of 576 is 24 units squared for this bottom triangle here. Now that we have the area of our bottom triangle, we can go ahead and solve for the area of our top quadrilateral. And since this is a cyclic quadrilateral, I can use Brahmagupta's formula. So therefore, I now need to solve for s again. And you may be like, well, we already solved for s. It's 12. Well, that's for the triangle. Now I need the s value for the trapezoid up here. And again, I need to solve for that s value because it's a different shape. So my perimeter will be different. So to solve for s, I'm going to use 5 plus 5 plus 5 plus 10 divided by 2. This will give me 25 over 2, which is equal to 12.5. So that's our semiperimeter for the quadrilateral up top, 12.5 units. Plugging it into Brahmagupta's formula, again, I'm replacing A, B, C, and D with 5, 5, 5, and 10, and S is being replaced by 12.5. So I'm left with the square root of 12.5 minus 5 times 12.5 minus 5 times 12.5 minus 5 times 12.5 minus 10. Simplifying down will give me 7.5 times 7.5 times 7.5 times 2.5. And of course, we take the square root of that entire chunk. Multiplying that out will give us the square root of 1054.6875. Of course, if you just enter this into your calculator with parentheses and all, it'd give you your final answer right away, which is about 32.5 units squared. Now that we have our area of our quadrilateral and of our triangle, we can go ahead and finish this off by finding the total area. The total area can be found by adding those two areas together. 32.5 for our quadrilateral and 24 for our triangle. That will end up with 56.5 units squared as our final answer. All right, guys, thank you so much for watching today. If you have any questions, please feel free to reach out, but enjoy the rest of your day.